Recording in
Shall I start, ma'am?
Sir, we will start within 5 minutes, sir.
Okay, sure, ma'am.
Good evening, everyone, and welcome to this session. Today, here we are gathered at an online platform for on Apple Online 6-day FDP 2024 to 2025, titled as Shaping the Future AI in Quantum Photonics, Nanotechnology, and Intelligent Signal Processing. A very warm welcome to all of you. I am working as an assistant professor in VITW Department of PCB, myself Roja. It is my immense pleasure to welcome you all today, and I would like to thank my beloved principal, Sir Dr. T. Venkateswar Rao Garu, my HOD, Dr. T. Vishnu Priya ma'am, coordinator of this event, and also my colleague, Dr. T. Hemalata Garu, for co-coordinator of this event, for giving me this opportunity. Good evening, Uma Desu sir, and welcome to the session. I request your permission to read out your profile.
Sure, ma'am. Please go ahead.
Yeah, thank you. Uma Desu is one of India's most visible AI, AI pioneer in India's transition into agentic AI and HR. He has trained and mentored over 35,000 engineering students, 1,300 faculty, and 5,000 MSMEs, making him one of the largest AI enablers in the country. Sir holds 75 plus global certifications from MIT, IBM, Google, Amazon, Microsoft, Oracle, Deep Learning.ai, and Dell. Mr. Uma is among India's most active AI speakers and educators, having involved in 40 plus high impact AI workshops nationally and internationally, delivering sessions in 25 plus FDPs among the 5 states of India and 40 plus chief guest and keynote addresses at national and international conferences and forums, influencing 45,000 plus students and faculty and professionals. Sir has also founded Interly India in 2004 and is acting as an active CEO since then. Mr. Uma Desu has 6 years of experience as head of sales intelligence in TCS, and Sir is currently working as the chief AI officer in Gen AI Pioneer. Apart from his this career aspect, Sir is also a content writer and author for 10 more plus books. Sir, it is my immense pleasure to invite you to the session. Thank you so much, sir, for giving me this opportunity. Please hand over the session.
Uh, Thank you, ma'am.
Thank you, ma'am.
So, am I audible?
So, am I audible?
Yes,
Yeah.
sir.
Is it repeating?
Sir, you opened maybe 2 logins, sir.
Ma'am, is it okay now?
Okay, sir.
Okay, fine. Just as backup, I just kept another one. So, thank you everyone for giving me this opportunity. And let me just share my screen as well. So today we are at foundations in AI, foundations of AI in ECE. Before I even come to this topic, I honestly have to admit one thing, that the topic of AI is actually being not driven by any software engineering expert or even Meta or even Sam Altman. Neither Meta, neither Sam Altman, or neither Bill Gates is driving the AI revolution. And when we say why AI is now an easy discipline, it's because AI has already shifted from software first to already hardware native. Because AI, the foundations of AI, we need chips, we need communication layers, we need real-time buses, we need, I mean, if you take the entire GPU, if you take Chat GPT or you take about Gemini, where are they running on? They're running obviously on Blackwell GPUs. So Blackwell GPUs, again, what is the whole basis of who is supplying it? It's NVIDIA. So entire AI revolution is being definitely being funded by the AC discipline. And this is what why we say that AI is actually an AC discipline. And it's not just, we are not just talking about GPUs. If you even go for autonomous vehicles is entirely an AC discipline. So autonomous systems entirely depend on sensor fusions, timing, and embedded machines. So it doesn't matter even if you have got a lot of wiring out there inside the bottom. See, for example, in autonomous vehicle today, we got around 7 kgs, 70 kgs of wiring. Now, even if you take out this entire wiring, you know very well in a car today, one sensor can make the whole car just stop. One small relay can make the car whole stop. And everyone who drives cars know this very well that the electronics are the most important part in the car. So you're not just talking about, autonomous systems, you're talking about even in general premium cars, which are heavily dependent on electronics today in the system. So AI definitely is an EC discipline today. And if you, instead of me talking, I just want to make you hear from obviously the world's most powerful person today. And the world's most powerful technical person is obviously not Bill Gates, but he is NVIDIA CEO Jensen Huang. So let us hear from him what exactly is this whole revolution of AI. And just let me put my
On a
sound there.
stage like this would tell you it is vital that your children learn computer science. Everybody should learn how to program. And in fact, it's almost exactly the opposite. It is our job to create computing technology such that nobody has to program and that the programming language is human. Everybody in the world is now a programmer.
That was Jensen Huang, by the way. So you heard him saying
It's
this.
just a miracle of artificial intelligence. The countries, the people that understand how to solve a domain problem in digital biology or in education of young people or in manufacturing or in farming, those people who understand domain expertise now can utilize technology that is readily available to you. You now have a computer that will do what you tell it to do. It is vital that we upskill it.
So that was Jensen Huang. You heard him very clearly. The whole revolution of AI is being definitely because of our EC discipline. So without the Blackwell GPUs, there is no ChatGPT, there is no Grok, there is no Gemini, there is no obviously AWS Bedrock. Every one system, every AI system runs on Blackwell GPUs. And today, you already know that the recently NVIDIA CEO is going around giving your in hand, he's giving this big Blackwell GPUs with the Hopper chips. It's a portable now. See, what was once upon a big GPU occupying almost in a data center space has now brought down to one small portable briefcase size GPU, which NVIDIA CEO himself is going to countries and handing it over personally. So that's the miniaturization that NVIDIA has brought about even in the EC discipline. So this is what we are looking at. EC is entirely an EC discipline and AI. In fact, we are not driving AI. In fact, the IT is not driving. Actually, EC is driving AI. So when you talk about the foundations of AI in ECE, we need to really admit it that AI is in fact an EC discipline. So AI workloads obviously are now shifting to DSP cores, NPUs, TPUs, FPGA accelerators. And if you even take FPGAs, when you compare to FPGAs or versus GPS, there are many instances where we are using FPGAs. So I mean, IT people, many 99% of IP people, they don't even understand FPGAs. But the jobs and all, if you take about AI infrastructure alone, you're looking at somewhere between 60 to 70 lakh rupees. Now, if I take even the top paying jobs, I mean, if I talk about the top paying jobs, nearly some 5 to 6 disciplines are totally AI EC disciplines, and not in fact. Let me just show you the top markets which are there. One small slide, I'll just slow. These are the top 30 AI domains, 40 to 75 lakhs. If you look at all these domains, you talk about number 3, autonomous vehicles. Again, the foundation is AI. Now, EC. And if you're talking about number 5, which is AI infrastructure and chips, again, it's again ECE. Talk about computer vision, the base systems, again ECE. You talk about VLSI AI, again number 10, it's always again ECE. So if you talk about mechatronics, again mechanical engineering plus electronics, again ECE. Voice AI, number 19, is again ECE. So if I look at this top 30 domains, I'm looking at nearly 7 to 8 domains entirely from ECE domain. That's what we are going to the foundation of all AI systems. See, whenever I go for AI classes with the engineering systems, so I tell them only one thing, that in fact you're not teaching, and you're not teaching how to program, but in fact you're trying to teach a machine how to think. This is and how to program itself, how to design itself. That is what their AI ECE engineer should be doing, and that's exactly what the future ECE engineer is supposed to do. So he is actually providing insights for a machine which has the capability of designing itself. This is where we stand today. We are standing at the throes or where we have already crossed artificial general intelligence, and we are ready to cross into ASI. In fact, if you look at all the Meta hiring, Meta has hired Matt Dateke for 2,195 crores. And this person is an AI researcher. And the reason he has hired him because they're pushing on ASI. See, ASI is artificial superintelligence, and ASI is nearly 15,000 times more powerful than the human brain. AGI is equivalent to the human brain. We actually are still at narrow AI, where AI does only one work, but if you look at the quantum breakthroughs which have been coming very recently, they are the marginal chips. Even if you talk about quantum computing, when you talk about quantum computing, we talk about the marginal chips. Microsoft will talk about that. And when Google talks about it, Google claims quantum supremacy only because they have been able to develop those Willow chips. Now, these chips which you are talking about, they can do, you know this very well. Now, the quantum, why they are claiming quantum supremacy? Because their chips can perform calculations which will take the world's most powerful computer 10 to the power of 25 years. Now, with this so much sophistication coming in the chips, it's obviously an EC driven domain. Entire AI is definitely an EC driven domain rather than what was earlier, nearly some 5 to 6 years back. We were only talking about AI, CSC, but now it's an EC driven domain. So we'll be looking at the next 1 hour, we'll be looking at how much AI has shifted the whole discipline and whole momentum towards EC. Now, if you talk about the classical digital signal processing system, so this is how your normal DSP system looks at. But if you look at today, if you every part, every decoders, you're looking at AI equalizer, you're looking at ML channel explanation, you're looking at deep reinforcement learning, working at the beam selection, and you're looking at AI decoded data. This entire part, entire supply chain, even if I take DSP as an entire supply chain is being driven by AI. These are the future which you are going in forward into, and it's not somewhere very far away 10 years from now. We are already in vogue, not in India, obviously not in India, but in several countries, and I'll present that to you. We are already ahead. Even DSP is totally driven now by AI. So we'll be looking at that as well. So what is AI replacing? Even if you talk about the core DSP, I'll start with DSP, then we'll move to more voice AI, we'll move into VLSI AI, we'll move into robotics. But let me just go through basics of how much AI movement is coming up. I know I've got limited time on this, so I'll go limited on this. See, the core idea is deep neural networks obviously can learn optical mappings. They can process functions directly from data. So that's the reason your typical, LDPC check codes, the ones which are this low parity, low density parity check codes. Now, normally, all this data which is used for coding, which entirely that was how it was being done using some algorithms like sun product or belief propagation. Now, what is happening? We have got is artificial neural networks, especially recurrent neural networks. See, when I talk about RNNs, as you know very well, basic definition of RNN is works very well in time series. So whenever there is a time series data, obviously it works. And you know very well, time series means electronics. Electronics signals, everything is about time series. So that's why we use RNNs very heavily in neural decoders. And then we also use graph neural networks because it's all the complex matrix of signals and wavelengths. We obviously use also GNNs. So basic definition of RNN, I'll give a very simple example of RNN because there are many people who might not be knowing what is an RNN. You can take an gossip chain. See, if I tell someone today he died, the next person will get the message he died because of this disease. When you talk about the third person, he'll get this message that he died of this disease and this person took this particular treatment, it didn't work. But by the time these 10 people go, the gossip chain is built. This is exactly the basis of RNN. RNN remembers the memory of the previous state. And that's the reason why in all time series analysis and especially in electronics, RNN forms very crucial role. We use RNNs for weather prediction. We use RNN for the entire algo trading. When you talk about the stock markets, the stock market entire algo trading is being driven by RNNs. Nearly 70% of trading on NSE is being driven by algorithms, and algorithms basis RNNs. So in the same way, in classical DSP component on the first part, on the LDPC side, we are totally replacing and outperforming neural decoders. I mean, the LDPC, we are replacing it with neural decoders because they can be drawn to decode faster and achieve much lesser error rates than your classical decoders. So this is one area which we are replacing LDPC. This is one of these DSP components. I'll talk about some of those other DSP components which we are replacing, and I'll take questions at 7:15. I'll open it up to questions. So next part which we are replacing many of the channel estimation parts. See, most of the machine learning models, they have been trained on a lot of pilot symbols and corresponding. In fact, many don't know that we have got models specifically for electronics. See, when we train our TC students, we normally train them on the TC students or EC faculty. We train them only on ECE specific models. There are ECE specific LLMs which have been trained significantly only on electronics data, massive data sets. So massive data sets. So you take those ML models. So the ML model will automatically learn the relationship between all the information which is coming in. So obviously what's happening is we get a better accurate estimate than your classical methods, especially when the conditions are not static, when the conditions are dynamic, especially in your mobile or rapidly changing channel conditions. So when we use ML models for this particular channel estimation, so normally what we are using mean square errors, the MSEs. So when we are looking at MSEs, instead of those MSE or minimum MSC, instead of that, if you use ML models, you're getting better outputs. This has already been proved. And we have been using it in several cases. In fact, one of these cases was done by one of our students as well, where he took this synthetic data and exactly did this project. The second part, ML channel estimation, was done by one of our students recently. Now, the third one, equalization. See, obviously, the third one is equalization. So, classical digital signal processing, equalizers, they look at the interference which is causing up and they try to equalize it. So, obviously, they use either MMSE or DFE. Many of it, obviously, I may not have deep knowledge about it because I'm not an ECE student, but only what I'm trying to understand and what we have learned when we teach ECE students, we only teach what exactly we are replacing, the AI students, where we are replacing, because unless we understand the domain, we obviously cannot teach even our ECE students. So we do definitely have a basic understanding about the entire DSP part. So where we are applying here neural equalizer, so what we are doing, we are learning to map the received signal. And what we are doing is any kind of a channel distortion or Gaussian noise. Gaussian, when we talk about Gaussian noise, so there are blurs we definitely apply, as in imaging we apply Gaussian blurs. So even in noise, in signals, when we want clarity, we'll add some Gaussian noise, but we are talking about non-Gaussian noise, where neural equalizers are handling non-linear channel distortions and non-Gaussian noise better than your traditional equalizers. So this is another area which is being replaced. Definitely not in India. In India, we have not come till this stage. So definitely this is happening, and I'll also tell you where we are doing this. The third one is system performance. Overall system performance, we definitely are using AI models, AI and machine learning models for comprehensive sensing of channel state information. So channel state information, obviously, because there's a lot of data which is coming in from all these transmitters and antennas. So obviously, all this data at this moment is coming to machines. There's no question about it. It's still coming to machines. But what's happening here is all these days, before the AI revolution, we never had an way of looking at all these huge data sets and try to deduce these insights. See, even if you look at computer vision, by definition, computer vision, the very reason why computer vision is mandatory for all ECE students, because every signal comes in some image format. All your wave signals, waveforms, they obviously come in images. So from those images till 2017, an image was an image, a waveform was a waveform, a signal form was a signal form. But today, a classical classical AI and current AI, if you talk about it, classical AI was still looking at that part. But 2017 onwards, we are able to deduce at what stage that particular signal is. See, recently, we did a lot of the sensor prediction and other projects. So where even at the wafer level, our team, our kids were able to deduce minute changes, especially because of computer vision. So we did these computer vision projects. So in these computer vision projects, we gave them a series of data, series of images. So this series of images, it allowed, we then perform this analysis using CV. So our CV systems could automatically detect the changes where there are wafer failures occurring at the chip level. So these are the kind of things which we are doing in EC thanks to computer vision. So in the same way, if you're talking about CSI, the channel state information, because a lot of this information is coming, and all this information might be coming in signal forms, might be coming in image forms, even signals we are converting it very easily today. So we are converting even 3D images, AutoCAD images are being easily read by AI systems. So AI signals, all the signals which are coming up, we are automatically converting it. We are converting all those signals, even audio signals we are converting. So we are converting images, we are converting all these waveforms and all. So all this information we are definitely converting thanks to computer vision. So AI is enhancing a lot of that part. And again, the last one, which is in beam selection, see deep reinforcement learning. So reinforcement learning is where a model automatically learns from mistakes and it starts to auto-correct itself. So here for us, when you talk about a beam selection, so in beam selection, you normally use in the classical methods, you use around an exhaustive search or a predefined beam code book or a precise CSI. So now what we do here, for us, it's an optimization. See, optimization, whenever we do, we either use DRL or we go for quantum optimization. So what we are here doing here in this case, in the deep RL case, so what we are doing is we train the model on all kinds of beam selection designs. So whatever data you have, whatever data sets you have, we train the model on all kinds of sequences. So once this data set has, when the model has been trained, once the RL algorithm has learned, it automatically allows for more proactive beam selection without needing any perfect or instantaneous CSI. So this really helps because more you train the model, it really helps for us to do even this part. So this is where AI comes into the picture. Now this whole part, whatever is being done manually or whatever being done by machines today, AI is currently replacing all of them. Now then you come to PH5. So I mean classical physics, obviously AI PH5 is one of the most important things, especially for electronics. So the traditional PH5 layer, obviously a merger of several optimized blocks, but now we are optimizing one by one using AI. So, and if you talk about autoencoders is now being used to replace the entire transmitter and receiver chain. So, network is being trained to minimize the reconstruction error. And this holistic optimization, in fact, recently, just last month, there was a white paper released where they're in fact using QUA, that's quantum optimization in classical DSP. That's a high-end topic, but I'm not going into it. But yes, even these optimization techniques in electronics, they're still being upgraded. So we are not just looking at classical AIC. Once upon a time, classical optimization. Last 1 year, we are talking about AI optimization. But for the next 1 year onwards, I mean, maybe around 1 to 2 years onwards, we'll be only talking about quantum optimization. So now you're talking about AI replacing classical DSP components, but in a year or 2 years from now, we'll be talking about quantum AI replacing classical AI in DSP. That's where we are now looking at. So if you look at all these advancements, they're obviously signaling a huge paradigm shift where data-driven learning is replacing model-driven design. So instead of writing complex equations for every component, the system is we can train the system on every one of these data or all scenarios on all wave signals. We can obviously train the system so we can go for better efficiency and with lower complexity and greater robustness. So EC today for us is the hardware, communication, and real-time foundation for all AI systems. So that's what I wanted to mention at the outset. So we have totally shifted from software first to hardware native. So this was the shift which is happening because today the entire discipline of CSC in couple of years, maybe around 1 to 2 years, will actually have to merge itself into other disciplines. This is the reason why AI is making it possible, because there will be no CSC specialization a couple of years down the line. There will be only an ECE AI, there will be an electronics autonomous vehicles AI, there will be a mechatronics AI, there will be an civil engineering AI, but there will be no CSE AI. And that's exactly the shift which is now you're looking at. AI is totally shift from software first to hardware native. And even if you take the placements in colleges today, today 1 CR in ECE is not a big deal. Earlier it might be a big deal, but today 1 CR or 1.5 CR in ECE is not a big deal. It's happening right now. Because AC, and in fact, many of you might also know, currently in the US, there's a huge shortage of electronics engineers. Because of the huge semiconductor boom, when these big companies like NVIDIA went to campuses, they were finding huge shortage. When they inquired it, because even in the US, just like in India, and mostly because our Indians are going there, everyone was speaking only AI. No one was speaking EC. So now this whole revolution is moving back. It's moving back to domain centric, to core engineering. In fact, EC, we don't call it core engineering. It's still in the main stream, but its AI is entirely shifting from CSC to core engineering disciplines. And EC and core engineering. I have to say EC and core engineering because EC doesn't want to be kept in core engineering. Some of the EC people, they don't want EC to be core engineering. So we'll keep it in the mainstream still. So AI is shifting definitely from CSC to down to core domains. So when I say hardware native, I'm talking about domains, the core engineering domains. So who is using this? Whatever I have spoken so far, the DSP part, who is using all these AI driven communications? So I'll talk about first the operator, the main brains, then I'll talk about the operators, then I'll talk about the companies which are supplying it. Now, obviously, Ericsson is the one. We talk about the telecom equipment vendors. Ericsson is using it. Ericsson is using it in autonomous networks. Nokia is using it in neural receivers. Hawaii is using in network automation. NVIDIA is using an entire RAN stock, SDR, and hardware acceleration. And Qualcomm is obviously using AI for beamforming and channel state improvement. This is what we're looking at slide number 2. When we're looking at CSI, it is Qualcomm which is actually doing it. So Qualcomm is integrating ML into their mobile chipsets for faster and more proficient processing of signal data and channel feedback. That's exactly what we were looking at slide number 2. And when you look at NVIDIA, obviously GPUs, GPUs and NVIDIA are well known. So I'm not talking about NVIDIA. So let's look at what Nokia is doing. See, Nokia is developing these AI-powered receivers to compensate for non-linear distortions in high-frequency CG bands. Ericsson obviously is using it for network issues and automatically self-adjusting parameters. See, one thing blindfolded we can say, predictive maintenance is one of the biggest drivers when it comes to telecom equipment vendors. So obviously, most of those first issue will obviously be predictive maintenance, where it's really used. Second thing is defect detection at the assembly level. Third is obviously wherever this fault performance is there, it's obviously going to be used there. But in DSP, especially if you're looking at, you have seen several components, and among all those components, you can see very clearly that Qualcomm is already using at CSI level. So at channel state information, Qualcomm is already doing it. So other components, yes, definitely, slowly they might change it, but yes, DSP is shifting to AI. So this is one statement which I wanted to make. So again, who are the users part? So operators, where are they using it? So operators, we are using AI in obviously for the, I mean, first, for example, if you take T-Mobile in USA, T-Mobile is developing the first American AI native wireless stack as a step towards 6G. They're not talking about 5G. We are talking about 5G. They are automatically talking about 6G. 6G obviously is heavily ECE driven. Yulo in Italy, they are automating their new 5G or standalone fixed wireless, I mean FWA network using autonomous frameworks. So in academia, obviously, the end-to-end chains are being driven by obviously with the top leaders. So your MITs, your Stanford, University of Pennsylvania. So they are doing a lot of deep research into differentiable physics and neural physics. In fact, if you talk about AI physics, AI or physics, AI or physics is the next $1 trillion opportunity thanks to EC discipline. And thanks to mechanical discipline, AI and physics is going to be the biggest research area in the coming years. So various university labs are leading their, I mean, research on DRL for dynamic spectrum. Especially, this is exactly what we have seen in beam selection. The fourth slide, which I spoke about, in beam selection, we are using deep reinforcement learning. But in fact, this particular slide, in 2 years from now, we will move on from deep reinforcement learning to quantum reinforcement learning. That's also coming. That's discipline. We'll also be moving very soon into that. So if you talk about who else is using, if you talk about defense and military, AI-driven DSP, obviously, it's real important, so especially in AI-driven electronic warfare, and especially for real-time signal classification, especially when you talk about enemies' communication signals. So AI takeover at the longer level, at the macro level, obviously the networks are driving it because AI is managing network operations, resource orchestration, resource allocation as well. See, in everywhere in electronics as well, or in electrical, resource allocation is definitely being driven by AI. So even in assembly line production, you are looking at resource allocation definitely being done by AI. Resource allocation earlier was manual, but now, no, the entire process of resource allocation, if it's mechanical engineering or electronic engineer or even electronics, entire resource allocation is being done by AI today. So signal processing, yes, AI is replacing the specific physical layers like the decoder and equalizer. That's what we have seen in the slide 2 and slide 3 and slide 5. So even the decoder and the equalizer, the 1 and 2 slides actually, sorry. So at the micro level, we are looking at AI replacing the specific physical layer blocks as well. And this is being driven by Nokia, Qualcomm, and academia. So this is what the entire level at the DSP side. So this is only one aspect of AI and ECE, but these are the fundamentals changes which are coming in AI. So if you look at 2025, where ACE and AI are converging, especially we are almost at the fag end, hardly around 25 days more. If you're looking at AI and ECA, AI for PHP, yes, entire classical communication blocks is being replaced by AI for PHP. And I'll be talking about that little bit. And yes, the momentum is towards 6G. Everyone is moving towards 6G in the entire, I mean, your global universe. We are not talking about 5G. We are only talking about AI native networks. AI on chip, you know it very well. Obviously, NVIDIA is driving it very heavily. So edge computing, everyone knows, I mean, especially the CSC engineers know that edge computing is becoming very big now. XAI and edge computing, they are definitely become very big now. So multi-agent network optimization, we are heavily using AI agents in network optimization, and I'll talk about where we are using agents in network optimization little bit later. I'll talk about it because I think we have a separate topic, agentic AI and autonomous vehicles. So we'll talk about that a little bit later. So VLSI fault planning, yes, definitely we are using machine learning. High-speed internet connect design, this is where all these trends are converging in 2025. So if you look at where EC is exactly meeting, if you talk about areas, now signal processing, as we have seen, CNNs, convolution neural networks, on spectrograms, deep learning based denoising, learn filters. So that's signal processing. If you're talking about communication system, you're talking about RL based MAC, AI. This is exactly what we have seen, RL based beam selection as well. CSI compression, we have just seen now. So embedded systems, we are using at edge inference, quantization, and tiny machine learning. So VLSI, wafer detection was one which I already spoke about at the assembly level. So we are also using PPA prediction, routing optimization, RTL generation. And you were talking about robotics and CPS. We are using sensor fusion for DL and RL based electronic control. See, when we're talking about robotics, this year's highest salary in India, entire engineering discipline is 2.5 crores. And this particular salary was not won by a CSC kit, it was won by an AI and robotics kit. So AI and robotics, obviously a lot of electronics involved there and a lot of sensors, a lot of computer vision, a lot of mechanical also involved there, and obviously a lot of reinforcement learning. So this is where AC and AI are definitely meeting. So when you talk about AI, so AI is replacing obviously classical DSP components. That's exactly what we are doing. Neural decoders at LDPC, ML-based channel recognition. This is exactly what we have seen just now. So what is this AI PhD? I mean, we are talking about AI PhD. So what artificial intelligence for physical systems, sciences and engineering. And where it's exactly doing, obviously 5G to 6G transition, that's where we are looking at. Some of these things we have already seen. So I'll just skip this slide. So I mean, where is this heavy, I mean, dependence coming from? So AI for PhD obviously relies heavily on scientific AI models. So looking at physics and from neural. See, again, as I said, AI for PhD is the next $1 trillion economy. The next $1 trillion economy is coming from the research into the combination of AI and physics. See, the earlier revolution was developed entirely. You talk about deep learning revolution, you talk about machine learning revolution. See, from ML to DL to even quantum, we were depending on entirely, I mean, take out quantum, we are depending entirely on algorithms. Algorithms, especially hugely mathematics. But the next revolution is coming in physics, and this is why AI for PHY, this is the why we call it is exploding. Because obviously the reason why we are able to do it, that we have now the ability to process huge data sets at very low cost because GPU computing cost has come down. And obviously, industry earlier needed a lot of simulations for design cycles. We are happily doing that in lesser cost. And traditional physics solving, I mean, if you talk about traditional physics, I mean, macro physics problems. So traditional physics problem was always complex, but AI plus physics is exactly what we are going to the next scientific AI, obviously the next $1 trillion space. So obviously many of these big companies, NVIDIA, MIT, they're already investing heavily into AI for science and AI for PhD, and is obviously being driven entirely by the ECE and physics discipline which is coming out. So in scientific simulations, we are using it, materials manufacturing, we are using it, digital twins, we are using it, climate earth twins, we are using it. So where ECE comes in. So when we are talking about ECE, we have to talk about obviously 6G. The entire 6G revolution, which is the first AI native communication standard, is totally being driven, obviously, by AI. So that's the reason why we call it the AI native communication standard. So AI max scheduling, AI-based dynamic spectrum access, IRS optimization using deep learning, beam prediction using transformers. See, we have already moved from CNNs, even in autonomous vehicles, we are no longer using CNNs, we already moved to vision transformers. So that also will be covering a little bit later. So if you look at all this, is 60 is entirely EC plus AI plus agents. So these are the three main components of 60. Without these three components, there is no 60 at all. So I mean, when we talk about 5G, 6G, 4G, we only talk about communications. But in 6G, it's totally different. It's ECE plus AI plus agents. And that's the topic for the next session as well, agentic AI. Agents definitely are going to play a huge role in the rollout of 6G. And I'll also be looking at why it really matters. So now what we are looking at, why it matters, 16 milliseconds. Now you're talking about autonomous vehicles. So when you're talking about autonomous vehicles, I'll tell a very small example. Very small example is a car which is going at 100 kilometers per hour. See, this 100 kilometers per hour car, autonomous vehicle, is a Tesla self-driving car. When it's going at 100 kilometers per hour, it has got nearly 4 sensors. Now, you've got ultrasonic radars, you've got millimeter radars, you've got also, I mean, where you're using Doppler methods also. So, when you've got three different radars which are causing all these signals, which are providing you sensor information. So when you are looking at all these sensors, And obviously you have the lidar as well. Lidar, without lidar is nothing is possible. So when you have these three different signals coming in, and you also have around 8 cameras. Now you have got 8 cameras which are sending in images. Maybe okay, let's look at vision transformer or CNN is transforming those messages. So now then you are looking at 16 milliseconds for a sensor capture. You're looking at only one particular say I mean the sensor capture is taking around 16 millimeter seconds. So then you are looking at CNN or vision transformer converting this whole sensor signal another 10 to 15 milliseconds. So now for tracking another 5 milliseconds. For fusion and making a decision part another 5 milliseconds. So this whole thing is sending to an control the brain of the vehicle. The brain of the vehicle is taking a decision in 10 milliseconds. So this entire 40 to 50 milliseconds is the entire supply chain of one processing of a signal or an image. So in this whole discipline, if EC side, no, that's the reason I talk about EC and autonomous system. If there is even a slight delay in these milliseconds, entire system will fail. That means this particular car, which has to actually slow down because the car in front is going only at 35 kilometers per hour, because EC has delayed it or a sensor failure has happened or EC has delayed that particular decision level or even processing of that. So the EC, even if it delays by 3 milliseconds, this car will go and hit the forward car. There's no driver involved here. There's only the brain is entirely being driven by the processing which is happening. So if the brain doesn't get the signal in time, it's obviously going to hit it. And that's the same thing even for lane change. So if the car is making a lane change without understanding whether there is some person, see if there's a car in the blind spot, the camera didn't capture it because there's no camera in the blind spot. Now, if the sensor signals are capturing it, if they're looking at distance, especially in you're talking about ultrasonic signals, ultrasonic sensor is actually detecting an object. Now, if this object is being detected and this particular object is not captured, that particular sensor data is not being captured here, what's going to happen is the car will automatically move into the blind spot because for it, there's no camera image coming in. It's only going by radar sensors. The radar sensors are not detecting an image, but that particular image information is not coming here. So in this particular that particular information is not getting processed, it's automatically the car will move into the blind spot. So real-time AI definitely in the autonomous systems it really matters a lot for us. Every millisecond totally matters because for us in the next second we are again getting 4 sensor data and again we are getting nearly not even next second, next 16 milliseconds we are getting again data, then we are again getting the computer image, 8 computer images and 4 sensors data. We need to process all these things in these 40 to 50 milliseconds. We are not talking about even seconds, we are talking about milliseconds. So this is the whole part where AI is mostly dependent on EC. Entire EC, I mean entire autonomous vehicle is totally dependent on electronics. So this is where we are using real-time AI. And the same thing when you talk about V2X systems for smart mobility. Obviously, beam steering, when you're talking about beam steering is being driven by machine learning, blockage prediction, network slicing. So all this has enabled us to take communication, the classical communication, which was always deterministic. We have now made it predictive. We are able to predict much ahead in advance. So from deterministic system to a predictive system, thanks to AI, is definitely being possible. So embedded AI, the tiny machine learning, that's what we're talking about. Yes, ma'am. Ma'am?
Sir, it's by mistake she on that audio, sir.
Okay, sure.
No problem, no problem, sir. Continue, sir.
So this another trend which we are talking about is embedded systems, embedded AI in tiny ML revolution. So obviously in predictive maintenance, keyword stopping, motor vibration, touchless gesture systems, and smart agriculture sensors. See, when you talk about any AI application, especially in computer vision, wherever computer vision is involved, the images are coming or the data is coming. You talk about IoT. Where does IoT get all its information from? IoT gets all its information from sensors. So, and all is what is sensor again, it's an EC component. So the entire AI revolution, whatever data it's analyzing, wherever, whichever format it's coming, is entirely coming back from the EC discipline. So obviously, you are looking at huge information which is coming to us. entirely from the ECE domain. Data is what we are processing in the AI domain. So DSP plus, AI driven DSP plus machine learning is what is currently driving 2025 trends. So obviously, from Fourier waveforms, we have moved to CNN feature waveforms. From wavelets, we have gone to multi-resolution features. From filters, we have moved to pre-processing. From modulation, we have moved to classification. So EC students, obviously, more than our CSE students, obviously EC students understand this much better. So what are the core AI models which you're using? As I said, RNN is obviously the best model which you're doing because entire waveforms are driven by this RNNs. So we use RNNs for LSTM, RNNs and LSTM for channel predictions, CNNs for processing those signals and spectrograms. We use transformers for CI compression, attention-based memo, autoencoders for denoising functions, obviously for denoising function and dimension reduction. And we are talking obviously graph neural networks for network graphs and routing optimization. We need to add another one, but that will be a little bit later. This quantum neural networks for optimization, routing optimization, especially the traveling salesman problem and other ones which are coming up. The entire routing part, we are actually using quantum neural networks this today. But again, that's another part. So what is agentic AI? Now let's go into this. We'll go into much more depth later on when we come to autonomous vehicles. So what do agents do actually? So what do agents do? Agents normally allow us to go beyond classical software. So now I'll give a very small example. So for example, if I'm getting around 200 emails per day, and I don't have time to go through those emails, I don't even want to even go through those emails, each of them. I want someone to actually read those emails, tell them which one is important, and if something is important, I want them to draw a draft for me and put in the draft for me and tell me that this is an important email, you need to respond. This is exactly what we are teaching today students, that agents can do it. So today morning also I was doing this session where students automatically created an agent. The agent goes into the Gmail, it drags the email, send it to an LLM. So in this case, a Gemini LLM. So the Gemini LLM is reading all those emails, summarizing them, classifying them, categorizing them, determining the urgency of it. Wherever there is an urgency, it will automatically creating a draft. And this drafts folder is being kept, the draft email is being kept in the drafts folder. And wherever there is an urgency, whether there is a critical signal coming from the urgency parameter, that particular message is coming to us through WhatsApp using Twilio. This is what an agent can do. So there's no need for someone to actually look at his email. Agents can do that. Agents can tell you which email is really important to, for example, if Vishnupriya madam is sending a message to me saying that you have an 6 p.m. Session today. I don't need to look at the email. The message is automatically coming to me from in my WhatsApp, because a WhatsApp message is coming through Twilio from the Excel sheet. From the Excel sheet is getting the output from the LLM. So this is what agents can do. So in EC, where do agents work? So when we are talking about real-time decision making, multi-step planning, memory-based optimization, tool usage, or autonomous orchestration. Another example which I want to tell before giving this analogy where agents can work or multi-agents can work. See, your classical Dasara sale or your Sankranti sale, which is done by Amazon, Flipkart, and other ones. Couple of years back, this was not even possible because they are delivering even in 24 hours. I mean, sometimes they might get delayed, but they promise 24-hour delivery. Now, how is this possible for just humans doing it or some software systems doing it? The days of software systems doing it are totally gone in Amazon, in Flipkart, and all these e-commerce companies, including Swiggy. Multi-agents are work. One agent is first, as soon as the order comes, one agent looks at that order. He determines where the product is, which warehouse is it. The second agent will take that information and pick up that, make that particular product wherever that warehouse is. It will look at the nearest delivery location, wherever is the nearest delivery location, and this particular one, it will do an optimization thing, and it will pass on to a third agent. And all these agents work in almost in parallel. So this third agent will automatically do it. It will update the customer. So at what time he is going to receive it. And the fourth agent will be tracking this whole thing. So this whole work, which was done by different individual machines, one single agent is doing it right now. And in fact, agent director is a new role which is coming to the market, where an agent is going to, and one person is going to direct nearly 500 agents. And these agents are going to do all the work, all the software work in the entire enterprise. This is exactly is going to be the future. Software systems are already being replaced by AI bots. And this is what, in fact, even Arvind Krishna is saying, are working alongside humans. Arvind Krishna has already said that IBM CEO. So AI bots are already coming. So these agents are already doing all this work. So in EC, when you talk about agentic AI, so network optimization agents, they are coming. Spectrum management agents, they are coming. Scheduling, as obviously scheduling and resource allocation, there has to be agents. Power management, predictive maintenance, obviously agents, multi-agent robotics. So I mean the same analogies which you see in other sectors, even in EC, we see the same thing. I'll give a few examples where exactly we can use agents in EC. So multi-agent systems in EC, I mean that's exactly what I was talking about. An agent director who sits in the top, and this all the other agents, they are the small agents, the tool agents which invoke the function, the environment agent, like your sensors and actuators, the coordinator agents, which are the edge to cloud orchestration. So now with these all are agents, and an agent director is sitting at the top. So and he's doing all the top line planning, and this exactly is what's happening in network optimization in NVIDIA, in Ericsson especially. This particular discipline has already come. Multi-agents are in full work. You can actually Google or YouTube. You can see these multi-agent systems working in network optimization, and this in the network optimization, these are the kind of functions we are looking at. So EC relevance, CPS, drone swarms, smart grids, intelligent transportation, and industry automation. This is what we are looking at in multi-agents. And when you're talking about AI and semiconductors and VLSI, and obviously one of the most fundamental aspect in AI and semiconductors, see not just the entire chip production. So obviously chip production time has come down thanks to ML. We are detecting faults. Obviously, the chip detection, wafer detection level as well, we are detecting the faults. We're also doing PPA prediction using gradient boosted trees, routing optimization, obviously using reinforcement learning. So verification, anomaly detection, we are using both variational autoencoders. We are also using ML pipelines. So layout synthesis using graph-based learning and ML-based hotspot detection in lithography. So this AI in semiconductors is a big market. And as you saw in our disciplines, in our top 30 disciplines, VLSI AI is at number 7. So VLSI AI 40 to 70 lakhs is not a big deal. Many people are getting it, and this is the reason why. Because heavily AI, VLSI combination of AI, and this is exactly what I was saying. This is only a matter of 2 to 3 years. There will be no CSC discipline at all, because there will be only a VLSI AI, there will be a mechatronics AI, there will be an autonomous vehicles AI. In fact, all engineering colleges will become this. I mean, this is what I predict, and this is the future of engineering colleges as well. Most engineering colleges will actually become domain engineering colleges. They'll not be engineering college per se, they'll become domain engineering colleges. AI is going to drive that. So there will be only domain-led in disciplines very, I mean, in the near future, that's exactly where the colleges are being driven. That's what we are driving the colleges, and all my network colleges, this is where we are driving. So we are asking them to become, I mean, we are starting at CBIT and other places where we are asking colleges to become domain specific. And obviously for EC, semiconductors and VLSI, for mechanical, we are going for autonomous systems. For electrical engineering, we are going for electric vehicles. So domain specific. So domain specific engineering is the future, and this is exactly where AI is driving it. So overheat, so one agent. So I'll give three particular examples of agents. So for this particular workshop, I just wrote 3 agents. So I'll just talk about those 3 agents. The first one is overheat detection in electronics. So this particular agent of mine, what it does, it will simulate real-time temperature monitoring in circuits using either sensors or simulated data. So I can use synthetic data, or I'll use the sensor data which you are providing. So whatever information is coming from sensors, I'll use that part. So real-time temperature monitoring, wherever I've got sensors. See, this particular part, overheat detection in electronics, we have used in nearly some 15 colleges so far. See, in colleges, especially in these labs, wherever this overheating is happening, we have introduced sensors thanks to visionary principals who have allowed us to do it. So wherever you have done EC training of students, we have already included this. So in especially labs, we have kept sensors, and this particular data is being monitored real time. See, many times you see this, especially in labs, these systems, even during lunchtime, no one is switching off the AC part. Even after the entire session is over at 4 o'clock, or sometimes in seminars, no one will be coming and switching off the ACs. This exactly what we have reduced in several colleges. So what we have done, we have used sensors in labs, we have used sensors in auditoriums, we have used sensors wherever there is a huge usage of these electronic items. We have used sensors to detect the, whether it's temperature monitoring, wherever the temperature is going up, real time, it's going off. The information is going by wireless, not even wired data. We have used wireless sensors. So these sensors are providing us real-time information, and we are automatically determining wherever there's an abnormal rise, we don't want them to fail. You know very well, despite the cooling system which is available in every lab, many of these labs suddenly shut down one fine day and not at pre-decided scheduled maintenance. The scheduled maintenance might be around once in 6 months. But sometimes in lab, and especially in engineering college, you know it very well. Sometimes a lab, especially that system, might totally heat up. The electronic system which is there outside, it will totally heat up, and you never know. It's nearly 1 to 2 months below the scheduled maintenance interval. So now these kind of things happen, and this is exactly what we are doing. Even in the triple E discipline, we have introduced sensors at several transformer level. At the transformer level, we have introduced sensors so that instead of the scheduled maintenance interval, which might be just before rains come in or after the rains are over, we are doing it peak demand. Especially in summer, we are doing it at peak demand. We have already started it in 5 substations today. In 5 substations, we have introduced sensors at the transformer level in nearly some each substation has got nearly some 8 to 10 transformers at the minimum. So we looked at the smaller ones because we wanted to initially first do it as a pilot demo. So this 8 to 10 transformers information is coming to us through wireless sensors. And this sensor information, our student who is sitting in the substation is actually decoding it. And especially we did it in summers actually, because summer is the biggest area, not in rains, but we did it in summers. So in summer, we reduce the peak demand much before the scheduled interval. So electricity departments are definitely happy with what the result was. They said they'll take it up, but obviously government works take a lot of time. But this is another thing what we have done, overheat detection. So we can definitely extend it to control fans. We can either cut off the power supply or alert the systems automatically. So predictive maintenance is one of the biggest differentiators where AI really helps. And AI agents really help a lot because AI agents take over a lot of information which cannot be done by classical computers. So that is one advantage of AI agents. We have used it in predictive maintenance across disciplines. I'm not just talking about electronics or electrical discipline, even in manufacturing. So even in manufacturing systems, predictive maintenance is definitely a go-go, because even in manufacturing, in assembly lines especially, if you run the machine for too long without the scheduled interval maintenance coming in, a system might fail. So even in manufacturing, these sensors can really help us detect when a system is getting overheated and when we need to actually do predictive maintenance instead of scheduled maintenance. So that's where we are using AI agents. So another one where we are using is auto debugging circuit checker. So we are taking circuit description or error queries and we are suggesting fixes for common mistakes. So this is another area which we are using. So we can identify issues like missing components or power supply errors. So what which really helps is, so someone who is working on Arduino boards or this simulators is just like at that time virtual teaching assistant. So it's built using rule-based AI and can be extended definitely with LangChain. And obviously, you can also use some Raspberry assistants again for this. Another one is voice AI, and voice AI is the biggest component which we want to talk about, because voice AI is a new identity. I don't know how much of you know about voice AI, but voice AI is a new identity. See, earlier we did it with biometrics, then we did it with Retina. Why voice AI is becoming the new identity platform? In fact, if you look at answer for that, you need to only look at the latest premium models of cars. In all premium models of cars, you are looking at voice controlled features today. So voice AI is looking at your voice and it's capturing your voice, it's recognizing your voice, and it's automatically taking those decisions. So voice AI is increasingly becoming the new identity beyond biometrics, beyond retina. And this is the reason why we are looking at a huge new discipline called voice AI. So voice AI, in fact, is another big area for us. And why the urgency? Why we are so much talking about urgency now? See what's happening here. AI is now obviously a part of our daily life. So everywhere we are using voice AI. So wherever voice AI is used, not just in, I mean, see, one question which normally people ask when I talk about voice AI, voices can be cloned. Voices can be cloned, no question about it. But at an frequency level, I'll just show that at a frequency level, voice AI can be a better ID developer than even your biometrics and retina. This exactly is why 94% of all large corporations are going to use voice AI in the near future. Verification is becoming more important, and voice authentication is the most non-invasive, natural, unique biometric, and which cannot be used or someone else can't do that. So we are looking at these several areas for voice prompting. So we actually teach the voice AI to our students as well. So what we use, why this is most important for us, because for us today, who is speaking is not so much, we recognize, voice AI recognize who is speaking, not exactly what is said. So what does it rely on? It relies on voice biometrics. And the reason why we decide on this, because every human voice is uniquely identifiable. So this is one reason why we have got this voice recognition. So where do we apply it, and why voice AI is so popular when voice can be cloned? That's one common question we normally get. So where we use it, we use mel frequency Kestrel coefficient. So we extract the MFCC features from short wave samples. We again use classifiers. So we use either k-nearest neighbors or we use random forest algorithms. Then we implement both enrollment and authentication flows. Then we emphasize the low resource CPU only performance. So the key takeaway what we see is lightweight but powerful. In fact, I can just show that sample as well for frequencies. I'll just show this project as well. So where we use these MFCC features and we can automatically do that. Again, this whole thing is obviously EC. So MFCC, I think the EC people know it very well. And why we use a MEL scale? Because MEL scale is more sensitive to low frequencies, which is exactly how our ears perceive the pitch. So it emphasizes the frequency bands that matter most in human speech. That's the reason we use MFCC. So what it does, and this is what we normally teach our students as well. So what do? We take an audio sample. We divide it to small frames. Then we apply FFT to extract the frequencies. Then we map these frequencies to the MEL scale. So what happens here is when we do that, we automatically convert this and we are able to recognize which particular voice belongs to the person whom we need to identify. So the audio signal is converted to power spectrum, Melfector band, and the MFCCs. So what we normally teach the students as well is audio input to feature extraction to model training, where we train the model on all these enrollment features. Then the authentication part, then that's how you authenticate a person after training the model. So this is what we are using exactly in industrial automation, industrial auto identification systems as well, using voice AI. So what we use here, we use Librosa, we use speech recognition, we use TensorFlow and PyTorch, and which companies or which who is using it very well. So this is what we use. I mean, this whole part, I just will just skip this part. But yes, definitely we are using it in a lot of areas. And these are the kind of projects which actually are doing in EC as well, in the top voice projects. And these are the projects which are fetching in number 8 position, number 14 position actually, voice AI. These are the kind of projects which we are getting our students to do so that they can happily move into that 40 to 50 lakhs positions. So these are all the areas which is being covered by voice AI. But again, that's another discipline, but it's entirely an AI discipline, I mean ECA discipline. So what does an agent do in voice AI? So voice control lab assistant, this is exactly what we are doing in agents. So real-time temperature monitoring in circuits using sensors, yes. So it allows users to give only spoken or typed commands for common lab procedures. So we are using a Gradio interface to take user inputs and a Gradio interface for the screen part for the user interface. So we are using a Gradio interface to take user inputs via a desktop. Then we'll return intelligent responses or actions. So it definitely helps us in improving the lab automation, identifying abnormal rise in temperature, and we can extend it definitely to other things like fans and all. So robotics, especially sensor fusion, we are using it very heavily. Pose estimation, deep reinforcement learning for control, predictive safety system, trajectory learning. Obviously, everywhere EC is used very heavily. So digital spins, we are using in smart cities, power system, transport networks. So what are the tools that when talking about the fundamentals, we also need to talk about which tools exactly every EC engineer must master. So when you talk about Jetson Nano, yes, obviously a must. You talk about Qualcomm RB5, you're talking about Corel TPU, area Infineon sensor kit, that's for the hardware part. Software part, we insist definitely on PyTorch, one compulsory thing. PyTorch, TensorFlow, definitely we insist on. MATLAB, anyhow, everyone learns. But we also use for SkyKit. SkyKit is one good thing, and there's a lot of EC that every AI engineer, EC engineer needs to learn. So obviously, apart from this, we also insist on deep learning, computer vision. So without computer vision, it's real hard for this whole thing to happen. So computer vision is one of the fundamental things. Apart from agentic AI, computer vision is another additional discipline that we normally teach, and we ask every engineer to master. So what are the certifications? Microsoft AI engineer, DC domain, JSON AI, or AC faculty who wants to switch over or go for some higher end projects. These are the certifications which definitely are needed. So hands-on projects, yeah, definitely RS petrograms here. So again, this is not relevant here. So I'll open this. We already are short of time. I'll open this for questions before I move on to the next session. Are there any questions? So these are the sensor technologies which you use in autonomous vehicles, lidar systems, radar systems, camera systems. I'll talk about when you talk about this navigation and localization. Obviously, we are using quantum navigation, high definition mapping, and GPS integration. So again, when you talk about quantum navigation, you talk about ECE only because ECE is driving the quantum navigation. So when you talk about quantum navigation, what we are talking about is usage of qubits. So usage of qubits for precise location, especially with the traveling salesman, when we are totally in a traffic jam, especially delivery robots, if you talk about it, delivery robots, if they're in a traffic jam, 4 routes, GPS can only give 4 routes. That's not northeast, west, south. But quantum, if I put instead 3 qubits in that particular delivery robot, I'll get around 8 routes. 2 to the power of n, I get around 8 routes. And if I put around, see, instead of 3 qubits, if I'm putting around uh, 5 qubits, I'm getting around 32 routes. So this 32 routes is what is being used in quantum navigation in trucks. Wireless trucks are using around 5 qubits. We are using around 3 qubits for delivery robots. So again, entire thing is being driven by sensors, by EC. So this particular traditional GPS system relevance is coming down, especially in the army, we are using it very heavily. See, I'll give a very simple example. Wherever there are jammers, GPS doesn't work. So now if you are going into an enemy territory and there are jammers, obviously GPS will totally collapse. And especially for aeroplanes, for fighter aircrafts, when they're entering enemy territory, GPS jammers will totally collapse. The jammers will totally collapse the GPS system. So that's where we are introducing quantum navigation in the defense, in all areas where jammers are present. So in all those areas, even in delivery robots, we are using quantum navigation. So that's one area which is very heavily used for us. Uh, any questions? It's already 7:18.
Requesting the participants to raise their voice if they have any doubts now. Thank you.
Yeah, any more questions? I'll be happy to answer, or you can just put in the chat window as well.
Good evening, sir. Hello,
Yes,
am I
ma'am.
audible? Sir, I have a question related to ML implementation in PPA enhancement. So related, sir. So if we want to train our models, so we are in need of database. But specifically for VLSI related kind of problems, it is very difficult for us to get the database. So for that, could you please suggest any kind of solution?
Which solution? I mean, can you just repeat that last part? In VLSI design, I understood.
Actually, I am working.
What was the help you were
Actually, I am
actually
working in the area of
looking at?
ML related to PPA enhancement, sir. My problem is I am not able to get a proper database to train the model. So I'm looking for that, sir.
So you're
So
looking for data sets, right?
yes, sir, data sets. So specifically
Data sets, yes,
related.
ma'am. I can guide you, ma'am. Just send me whatever data sets you know. There's a huge data sets on electronics. We have got enough data sets. And in fact, there are specific websites only for electronics AI. I'll send you that link. Just send me on WhatsApp. I'll send you that links, ma'am.
Related to PPA, sir. Related to PPA analysis, can we have the data sets, sir? Hello.
Sure, ma'am. Just send me that requirement.
Related to PPA enhancement only, sir. Actually, I tried some statistical methods like simulated annealing for floor planning like that, sir. So specifically for placement and routing, if I want to perform any kind of ML involvement, I'm not able to get the database, sir, to train the models. So I'm not able to get the database. So where can I find the database so that I can use and I can train my model for placement and routing related tasks?
Sure,
So,
ma'am. Yeah, you can just contact me, ma'am. I'll give you the links to those data sets, or I'll just give you the download links for those data sets. You can happily take it.
okay, sir. Okay, sir.
You are in VITW, ma'am?
No, sir. I'm a participant in this workshop, sir.
Okay, you are a participant. Okay.
Yes, sir. I'm a
Just send me on
participant.
WhatsApp, ma'am. I'll just give my number in this. Okay. So I'll just give my number. Just send me a DM and I'll share those data sets link.
Yes, sir. Sure, sir.
And if there's a WhatsApp group, ma'am, I can share it so that everyone can also look at it. I'll send it to ma'am. She can post it in the WhatsApp group as well.
Yes, sir.
That's my number.
Yes, yes, sir. Yes. Thank you, sir. I will contact you, sir.
Yes, and even for training, ma'am, please use AI specific, ECE specific LLMs. Don't go for those normal LLMs. We have got enough LLMs which have already been trained on huge data sets of electronic signals. So please only use them, and they are downloadable. You can happily download to your desktop, and you can do it this entire thing without needing any API keys. You don't need to pay anything for API access. You can happily download them and do this entire model training on your desktop.
Okay, sir. Okay, sir. Sure, sir. Thank you, sir.
Any other questions? So just summarizing this part, foundations of AI. So next we'll move on to autonomous vehicles, agentic AI. So obviously we are going to have a 5 minutes break, ma'am. Can we have a break at 7:25? Vishnu, ma'am? So
Sir?
is everybody- Yeah.
Sir.
Can we have a break at 7:25?
Yes, sir. By 7:30, we will start the session, sir.
Yes, ma'am.
Mm.
So any other questions, you can just continue in the next session. We'll take a 5 minutes break and we'll come back at 7:30.
Dear participants, let's have a break for 10 minutes, and the session is going to start around 7:35. Please stay in the same link. The session will start by 7:35.
India aims to harness the power of quantum technology to drive innovation, strengthen national security, and revolutionize industries, positioning itself as a global leader in this cutting-edge field. Across the world, nations are racing to master quantum technologies with its deep scientific expertise and strong innovation ecosystem. India stands at a defining moment in its quantum journey. The National Quantum Mission gives India a powerful platform to contribute globally, impacting healthcare, cybersecurity, and capacity building to establish India's leadership in quantum science. The National Quantum Mission has laid out specific time-bound objectives. Quantum computing evolution. Develop intermediate-scale quantum computers. 50 to 1000 physical qubits in 8 years, using different technologies such as superconducting and photonic-based qubits. Long-distance quantum secured communication. Establish secure quantum communication across 2000 km within India, both satellite and fiber-based, and extended for international connectivity. Multi-node quantum networks. Develop a scalable multi-node quantum repeater network using quantum memories and entanglement distribution. Advanced quantum sensing and metrology. Develop high-precision quantum sensors and quantum-enhanced imaging systems to enhance navigation, imaging, and national security. Quantum materials and devices. Design next-generation superconductors, semiconductors, and topological materials for building quantum hardware and detectors. To operationalize this ambitious vision, the National Quantum Mission has established 4 thematic hubs, each dedicated to one core vertical of quantum technology. At Indian Institute of Science, Bengaluru, the Foundation for QC Innovation, India's Quantum Computing Thematic Hub, is advancing India's quest to build indigenous quantum computing technologies. Its technical groups are focused on developing scalable quantum processors across superconducting, semiconducting, ion atom trap, and photonic platforms, while building secure and accessible cloud infrastructure to support research and industry needs. At IIT Madras, in collaboration with C.The IIT M.C. Samagnya Technologies Foundation serves as the Quantum Communication Thematic Hub. Here, researchers are developing quantum-secured communication networks across fiber and satellite platforms, QKD systems, photon sources, and quantum repeaters, nurturing startups that will secure India's digital infrastructure for defense, finance, and governance. At IIT Bombay, the QMAT Tech Foundation, Quantum Sensing and Metrology Thematic Hub, is redefining precision. Its technical groups are building quantum magnetometers, NV Center-based quantum sensors, and quantum-enhanced imaging system, establishing national quantum metrology standards and translating these innovations into applications for healthcare, navigation, and imaging. At IIT Delhi, the QMD Foundation, Quantum Materials and Devices Thematic Hub, anchors India's quantum hardware ecosystem. Its technical groups are synthesizing next-generation superconductors and topological insulators, fabricating single photon sources and superconducting circuits, and building India's quantum hardware manufacturing base to support all other hubs. Selected through a rigorous national evaluation process, these 4 hubs bring together 14 technical groups with 152 researchers from 43 institutions across 17 states and 2 union territories. The mandates of each thematic hub are technology development, human resource development, entrepreneurship development, and international collaborations. Each T-Hub follows the hub-spoke-spike model, connecting universities, R&D centers, and industries in a powerful collaborative network. This model accelerates research translation, encourages knowledge exchange, and builds a strong ecosystem where India's quantum vision comes alive through partnership and purpose. In this series, we will outline the work being carried out at each thematic hub, including their research directions, laboratory facilities, and development plans. This will offer a clear understanding of how India is building capability in quantum technologies. 1. Theme. India aims to harness the power of quantum technology to drive innovation, strengthen national security, and revolutionize industries. positioning itself as a global leader in this cutting-edge field. Across the world, nations are racing to journey. The National Quantum Mission gives India a powerful platform to contribute globally, impacting healthcare, cybersecurity, and capacity building to establish India's leadership in quantum science. The National Quantum Mission has laid out specific time-bound objectives. Quantum computing evolution. Develop intermediate-scale quantum computers. 50 to 1000 physical qubits in 8 years, using different technologies such as superconducting and photonic-based qubits. 152 researchers from 43 institutions across 17 states and 2 union territories. The mandates of each thematic hub are technology development, human resource development, entrepreneurship development, and international collaborations. Each T-Hub follows the hub-spoke-spike model, connecting universities, R&D centers, and industries in a powerful collaborative network. This model accelerates research translation, encourages knowledge exchange, and builds a strong ecosystem where India's quantum vision comes alive through partnership and purpose. In this series, we will outline the work being carried out at each thematic hub, including their research directions, laboratory facilities, and development plans. This will offer a clear understanding of how India is building capability in quantum technologies. 1. Theme.
So welcome back. We're moving on to the next session. Ma'am, can I start or should I wait?
Okay, sir. Continue, sir.
Sure.
Hmm.
So we on to the next session, and the next session obviously is agentic AI and autonomous systems. So when you talk about autonomous systems, I need to go into basics of autonomous driving. There's one thing which we need to introduce before we talk about autonomous systems. So let's understand the basics of autonomous systems before even we go into agentic AI and where agentic AI really helps. So what we talk about the basics of autonomous systems, the basic thing is this whole thing is possible because of one thing, CNNs, deep learning really help, transformers really helps, sensors, computing entirely safe for transportation. Smart transportation is what we talk about. So autonomous vehicles, they're collecting real-time data from cameras, from sensors, and from radars, LIDARs, ultrasonic sensors, IMUs, GPS specific, wheel encoders, thermal sensors, and you're not talking about the sensors which are already there within the car for car maintenance. Especially if you talk about ADAS, it's again a huge segment we are talking about. So interior driver monitoring cameras that also have come up right now. So where the driver fatigue is also being captured. So now this all this information is coming to us in milliseconds. So in this milliseconds, so much of information is coming up. So obviously, one simple query which needs ones to raise, where is AI here? In fact, this is all electronics. There's no AI involved here. This is entirely electronics. Before AI becomes intelligent, the electronics must become fast, clean, synchronized, and reliable. Without electronics and without electrical engineering, autonomous vehicles, AI is nothing at all. We can only work when we get data, and the data is coming to us from electronics. So autonomous vehicles is obviously, that's what we call a sensor factory which sends signals to the computing factory, which finally gives an signal or an controlling the brain which is controlling the whole autonomous system. It's getting the decision inputs. So sensor factory, unless it gives us the inputs, the computing factory doesn't work. So now if you talk about ECE, ECE has to send signals to AI, AI has to send signals to a neural network which is sitting there. Again, it's a AI component, obviously. So sensor factory to compute factory to control factory is autonomous vehicles. So this is entirely the domain of electronics industry. So how many cameras? Normally, how many cameras do you use? We use around 8 cameras. So front camera one, front narrow one, front wide one, side cameras two on each sides. But this side camera doesn't capture the blind spot. Rear camera one. So you're looking at 8 cameras. So these cameras, if you look at the front one, long range, front narrow is high speed, front wide for junctions, side cameras for blind spots. This is in fact present only in the latest models. That's in the 2025 models. Otherwise, blind spots in the previous 24 models were not present to us. Rear camera, reverse and rear tracking. So you're looking at frames per second. You're looking at 36 to 60 frames per second, and you're looking at front narrow 60 frames per second. That means at a rate of around 200 to 500 Mbps. See, all this much data. Again, it's not just a wiring which has to provide so much of an internet access to the sensors, but it's also the processing part. Once all the signals, sensors are being generated, you're looking at cameras alone generating around 36 to 50, 60 frames per second. So who is going to do it? 8 to 12 cameras, bandwidth itself is 1.5 to 2.5 gigabytes per second. That means the CNN in the system, now it's in fact a vision transformer which is doing it in the latest models. So a CNN must process around 2 gigabits per second of alone image. I'm not talking about sensors. About images alone, it has to process around 2 gigabits. Now, how fast do CNNs process? This is exactly what we had seen in this previous camera as well. Previous where also 16 to 33 frames from the has to happen in 20 to 40 milliseconds, including the sensors being used processing as well. Of blind driving. Almost 1. And even if this, we are talking about 100 milliseconds, 10 milliseconds delay, you are losing total transform into another 10 milliseconds in the next cycle. So obviously this is a domino effect which talking about 25 to 30 decisions which are being
Excuse me, sir. Sir, your voice is not audible to us.
ma'am.
Yes, sir.
Yeah, let me just keep a backup just in case. Give me a minute.
Yes, sir. Yes, sir.
I'll just keep a backup on my phone as well.
పెన్ కావాలి నాకు అందుకని
Okay. So radar sensors, angle part, and again you're talking about sensors which are giving us, then you also have LiDAR obviously the most useful thing because it creates so vertical beams. Okay. Am I audible?
Yes, sir.
Okay, fine.
Yes, sir.
So LiDAR creates the 3D point clouds. That's very important for us, especially in night driving. So LiDAR gives us the shape, distance, even at night times. The next one obviously is ultrasonic signals. So ultrasonic signals helps us in short range precision. So the cheap, useful definitely because see again, when you talk about signals, when you talk about these sensors, kindly understand there's also a huge electrical engineering component which is involved here. Every one of these sensors, every one of these cameras, they operate only on low voltage. So that means the entire automobile part is operating on high voltage. Your car AC and the engines, they are working on high voltage, and this entire electronics part is operating on low voltage. That means entire wiring of the car also has to separate high voltage and low voltage. In fact, we then we also use the IMU plus GPS. And in fact, in latest cars, we have moved beyond GPS. We are going to directly to quantum navigation. So IMUs we use especially in areas where GPS fails. So wherever the GPS fails, IMU helps us keeping the car stable between frames. So the sensor fusion is one of the biggest challenges, obviously, because each sensor has got a different refresh rate, different data size, different noise profile. So your electrical architecture, its job for us is to ensure synchronous power supply. See, wherever there are spikes, especially high voltage, low voltage, for example, a high voltage wire is getting overheated and it's just beside the low voltage wire, the sensor will totally go out of control. So even a small sensor, so the electrical architecture needs to ensure that it doesn't get overheated. Now, when you're talking about overheating, kindly also understand that the cooling system of the engine has to be different from the cooling system of this entire electronics part. The entire low voltage electronics of the autonomous vehicle, including the brain, which is processing all this definitely has to a separate cooling part. So these are the kind of challenges which are present in an autonomous vehicle. That's the electrical vehicle, electrical engineering will take care of it. But if electrical engineering fails, electronics fails. If electronics fails, AI fails. So all these three are interrelated. So you have several interfaces because cameras have to interface with Ethernet, radars have to interface with Ethernet, LiDARs also are dependent on Ethernet. So all this wiring, obviously, any electrical subsystem fails, entire thing drops. Camera frame will drop, LiDAR point will totally go wrong. The radar return is delayed. So this decision is delayed. So autonomy or autonomous vehicles is obviously not possible without a synchronization between the electrical circuits and the electronic circuits. Only when these two come. So if you talk about the order, electrical, next electronics, then AI. AI comes actually at the third part. So AI is obviously dependent on your clean power rails. It's dependent on your signaling. So it's also depending on synchronized clocks. is depending on serializers, and it is dependent on your stable sensors. That means I am dependent totally in an autonomous vehicle. If I am making the decisions, I am totally depending on a sensor which is working properly. If a sensor is not working properly, if it's not if it's an overheated sensor, I'm obviously going to get the wrong data. So without the sensors working inside the autonomous vehicles. So obviously you're talking about the cameras because they capture the eyes. I mean, entire high resolution cameras. They are providing, as I said, there are 8 cameras which are available. This is the lidar part. So lidar obviously employs this laser beams to generate high resolution 3D maps of the surroundings so that the vehicles can identify obstacles and navigate very effectively in various environments. So this is more important because you're looking at it, the lidar case alone gives us all this, and obviously the electronics part. So if you talk about radars, especially if your radar technology is using excelling all weather perception, especially for navigation, these are all obviously electronic items. And you talk about ultrasonic sensors, obviously for everywhere. Obviously they're cheaper, but they really help uh, autonomous way accurate distance measurements. So they are also used for us in ultrasonic sensors. IMUs we already seen. So another one is GPS tech. But GPS RTA helps us and already. So if you're looking at this entire architecture, this is all electronics. RTK, your HD maps, they're really crucial for maximizing the environmental awareness, enabling the vehicles to detect and respond to surrounding objects. So if you now you spoke so much about all these parts where you are getting a lot of inputs. Now, who is processing all these inputs? That's the next question we need to understand before we go into an autonomous vehicles. So once we have to understand it, there are 3 brains. See, now if you take a normal vehicle, how do we do the humans do the driving part? Give me a moment. So if we are the humans, so we have this, we use around 3 sensors, which is our eyes, ears, and brains. Obviously, the 4th sensor we use are the hand and foot movement. So if you take at it, if you look at it, we are using actually 5 sensors. From the eye and the ear, there are perception sensors. So in this perception system is being replaced in the autonomous vehicle by a radar and a camera. Now the second part, this whatever you are looking, whatever you are hearing, someone is sounding a big horn. We are hearing that. And in fact, in India, when you put an autonomous vehicle, sound is not being captured. In no model today are we capturing the honking. I mean, India, we now, alert people by honking. No autonomous vehicle till date captures sound. So that's another development which someone can actually look into, especially when he's doing this autonomous vehicle. Till date, because in foreign cars, obviously there is no honking of sounds in foreign roads, but in India, honking of sounds is a major problem, and it's obviously keeps on happening. So that part is no longer available because we also listen. So we do have a radar and a camera, but we don't have the honking part. So the radar has to perform that particular part. because radar is detecting that part if some vehicle is coming up. But yes, we definitely need an improvement there as well. So the brain, the decision making unit, is exactly what we are going to look at. It's going to do it. So who makes the, once the decision is made, who is in there in the controlling session? See, controlling we normally do by our hands and our legs. So we apply a brake or we accelerate speed and we move the steering. So those parts are being done by three. That's an anti-collision system, an electronic stability system, adaptive cruise control. So they are the brain behind an autonomous vehicle. So this is the what if you look at speed detection, and these are what you're looking at. These are all the radars and signals which are coming in. Now the simple question is, the biggest problem for an autonomous vehicle is changing lanes. See, when the autonomous vehicle is going straight, it doesn't matter at all. It can happily make a change. Some part we can definitely, and you can, when you are trying to make a change into the next lane. So now in this vehicle, it has to move till here. That means it does not need this data alone. The vehicle which is in the front, it has to get the vehicle data of this particular vehicle which is there in the back in the next lane, and it also has to determine the speed of this particular vehicle. Without determining the speed of this vehicle and this vehicle, it definitely cannot make an change. See, the human brain is still doing that very intuitively. The human brain is looking at it, it determines automatically, the brain automatically determines what speed the car in the backside is coming. It can, there's enough margin, I can happily go there. Now, an autonomous vehicle, if it's going at 80 kilometers per hour, and this guy is only going at 30 kilometers per hour, and the margin is only around 4 feet, obviously by the time this guy and comes here and makes a break, he's going to go and hit this guy. So this is the biggest challenge for us in making lane changing behavior, is the biggest challenge. And that's the reason why we need powerful computer vision, especially not just the sensors part, because sensors you can see very clearly. It's not just a sensor and cameras giving us just the outside part or the front vehicle. You also need to capture so much of information to replace an human. And this particular part, if you look at it, how this transition is happening. So this is the road. We are looking at the road images. Then we are sending it to a CNN. So CNN, if you look at the convolution neural network, so what it does exactly, you take this whole image, we break it down into small 3x3 matrices. So once we break down the grid, we apply this CNN function at each of those 3x3 matrices by sending a cell filter. So by sending a filter, we do this CNN decision. Once we do the multiplication, that's exactly the working of a CNN, but actually it's not important. But I'll just give one small thing, just 1 minute thing, how we exactly do. So this 3x3 matrix is multiplied with a small 3x3 this we take a 5x5 or a 3x5. By 5x5, we multiply with the 3x3 matrix, and this 3x3 matrix we get a figure. So that figure is the most important detail in this particular part. That's why we do the entire image, CNN done, and after doing CNN, we do go for pooling. So in pooling, we definitely do more downsampling. So what it exactly does, the CNN process, it gives us an image. It gives us an image, which image classification input, and you're talking about 8 images coming around 36 frames per second. That means you're talking about more frames coming a little bit ahead. So now that's the reason why the car have to be real. Say, I'll give a very small example of this CNN part so that you understand what's the deep learning which is behind an autonomous vehicle. So now these images, one image is coming, we do the apply the comment. See, this is a 62 by 62 image. So we take this image, we apply the relu function which takes out the irrelevant details. That means if there is a ditch beside, I just drop it. If there's a dead end, I drop it. Then all this negative part is removed. Then I apply the second convolution layer. So automatically it keeps on reducing. Then I go for max pooling. So in max pooling, actually I will show you what happens in max pooling. So max pooling, what happens here? Each part we take an 2 by 2 matrix, and the 2 by 2 matrix we find what is the maximum number in that, so that what's the maximum feature which is available here. So this is how we are rotating a 2 by 2 matrix. So we take look at this, what's the most important feature here, then we get the max pooling there. So this kind of max pooling is done nearly 3 times. So you're looking at max pooling function 1, max pooling function 2. By the time this whole process completes, we are down to an image. So now this 60 by 62 by 64 by 64 image is boiling down. If you look at it, it's almost coming down to a 13 by 13 image. Now this 13 by 13 image, it's not audible. Sir, am I not audible?
Sir, it is
Professor,
audible, sir. No problem.
Message saying that I'm not audible. That's why.
That is previous.
Sorry. So if you're looking at this, Amit sir, okay, fine. So you're looking at so many three convolution layers reducing this 64 by 64 image to a 13 by 13 image. And this 13 by 13 image is the one image which is going to be classified. And obviously, see, image classification doesn't have a three-dimensional image. So we again bring it down. We apply a function here. We totally multiply with an softmax function, and the softmax function multiplication brings down the classification down to a single dimensional image. And single dimensional image is what is being taken down here after this function for the final classification that it is a spool bus. So now you're talking about 8 images which are coming here. So this is the flattening layer. The max pooling function, we do a flattening layer, then we apply the softmax function, and then only we do the image classification. So you're talking about here 8 images, 8 such images being processed. 8 such images being processed. And who is doing this process? The CNN is doing it. Earlier it was the CNN. Now it's a vision transformer which is doing it in the latest model parts. So now this whole process, as I said, entire interference is happening in totally 10 to 12 milliseconds. So 10 to 12 milliseconds, every image is being processed. So now you're talking about this and a car, an autonomous vehicle, taking around 25 to 30 decisions per second. Now you're looking at that much level. That means the CNN has to be so fast in processing this whole thing. So when we talk about EC's importance, at the same time, EC sensor data or EC camera data is coming down to us in the computing part. So once the computer is done, then we come to the perception brain. That means whatever the sensor data is coming, giving us, we are processing that particular data to understand and whatever create a comprehensive understanding about our surrounding environment. In this case, this is actually computer image part for image detection. So this perception brain allows us to process the sensor data and create a comprehensive understanding of the entire environment. So 3D point clouds which are coming from 3D clouds which are coming from the lidar, or you're talking about ultrasonic sensors, or you're talking about the radars. So all this gives us a whole overview of where this particular car, where you are in middle of what. So that really helps in understanding us from the perception brain. Now, all these sensors data, as I said, there are multiple sensors out involved there. These all sensors are integrated in a fusion brain. So there's a second brain which does this fusion brain. This combines data from multiple sensors for enhanced accuracy. So with multiple, you're talking about 4 sensor data which is coming up, and this particular sensor data is being fused out here so that we get a more accurate representation of the driving environment. Next part is a prediction brain coming in. The first brain, which is making perception of it. The second brain, which is doing the fusion of it. The third brain, which is actually doing the prediction. What action needs to be taken. So we need to do the forecasting of other actors, not just our acting. So now we need to forecast at if I'm in the left lane, that car is coming at this moment. I can't make a left lane because there's a car which is coming very fast. So the prediction brain forecasts the behavior of other actors in the environment to anticipate potential conflicts and plan accordingly. So this is what the fourth brain does. Now, once is the third brain does, the fourth brain is the one which is actually the ears and the feet, the hands and the legs, which is the control brain. So the control brain is finally what various sensors to execute actions that ensure that the environment. inside the engine. They'll totally all these sensors, information, and all they obviously said there are only two places where we can place them. One under the seat, but most cars, if you talk about Waymo and all, we place them directly under the dashboard. So inside the dashboard, that's where we place them, and that's where your computer brain actually is located. This particular brains. So this is the autonomous system pipeline. So sensor data, which is coming at end-to-end architecture, you're looking at this. Then future, yes, obviously there's a lot of future in autonomous vehicles, but I just before doing this, I'll just go through one particular slide so that for you to understand how these actually look like. Give me a moment. I'll just close this. Just close this as well. This as well. And yeah, this is actually an electrical presentation. I'm not just doing it now, but I just wanted to show you. This is the separation we have. The high voltage cables, the low voltage cables, we need to separate them. And then, so this is how we do this for complex wiring of vehicles. You are looking about 3 to 5 kilometers of wiring, about 70 kgs plus. In luxury vehicles, you're looking at around 7 kilometers of wiring. So all this wiring has to be done. So now again, this particular car, when talking about sensors especially, whenever you're going under a high voltage line, so whenever you're going under high voltage grid, in fact, we have done this experiment. We have taken it under high voltage line, especially in this particular area of BTPS area, where we've got a huge number of high voltage lines across fields. We have taken it under them. We have witnessed GPS interference. So that definitely will come. GPS deviation will definitely come. Radar will pick up different noise. EMI coupling sometimes really happens, but it's not big a thing, but really some GPS effect is. So this electromagnetic interference, again, there's a combination of electronic and electricals. So both needs to understand this electromagnetic interference definitely comes from these high field lines, and this particularly drops in the sensors. So this particular electromagnetic, so when you're talking about, okay, I'll just leave this part, EMI mitigation and all, I'll just leave this part for sensor technologies. So let me just look at this sensor technologies. This was what I was talking about, quantum navigation. So quantum navigation is also coming very heavily, but what I wanted to show this this one. Just a minute. So that's fine. I'll just come back to our main presentation. By the way, just wanted to show earlier part, I couldn't show you some of that part. Voice authentication system present to you, how it actually can. So what we do here, we take the samples, we break it down around model trains all these models. So we have got these several samples, around 30 of them. So now the 20 MFCC features, we are extracting them. And once these MFCC features are extracted, is trained, then we automatically, when we give the authentication sample, the authentication samples, the model checks against the training part. So then it will tell which particular person voice AI. So that's one thing which I wanted to show. I couldn't show it earlier because I couldn't pull up this. The other one which I wanted to show, especially in waveform analysis, this series, I'll just take 5 minutes here. So in waveform analysis, where we use computer vision, so they use waveforms. The second part where we use especially is in noise spike oscilloscopes. This is one project which we have done very heavily, and especially in labs as well. So in oscilloscopes, even a small noise, normally in classical computing or manual detection, some noise spikes are not actually detected. Those noise spikes really cause a lot of difference in oscilloscopes. So this particular noise comes. So what we have taken a normal oscilloscope wave signal, and this wave signal we have passed it to our program. This is the waveform. So this waveform, when we pass it to our particular program, we automatically are able to detect the noise spikes. So this is where AI really helps a lot. So in several areas like this, it definitely helps a lot. And even in the VLSI level, wafer detection. So this is another wafer detection where we using CNN. So we also do this wafer detection, and we automatically test the accuracy part of this. So these are things which we do using AI. So I just wanted to go through them. Sensor failure in autonomous vehicles, we do a lot of AI usage in sensor failure, especially as I said. I gave a very small example. When it's passing under a high electric vehicle circuit, there's a possibility of failure. There's a possibility due to electrical impulses. Electrical engineering, it has a problem. Whenever there's an overheating of cables, the sensor can fail. Now, is there an autonomous system? So where is AI coming into the picture? Now, can I predict? Now, this is what we are doing here. So can I predict even in an autonomous vehicle when a sensor is going to really fail? This is one of the autonomous vehicle challenges which so far has not been done, but yes, we are working on it. In fact, some projects we are working on it. Can we detect? I mean, if we introduce a system, again, this is an hypothetical scenario which we have been testing still. It's not a completed scenario. So now all this wave data which is being processed by the brain inside the autonomous vehicle. Inside the autonomous vehicle, a lot of data is being generated continuously by the sensors, right? So if this particular sensor data is fed wirelessly outside the system somewhere where we can do an analysis, because already this brain is already loaded. And this fact, in fact, we have tested it on electric vehicles. We have taken this project to several autonomous vehicles. They refuse to include this particular part inside the autonomous vehicle brain because the brain is already loaded. But this is something which we are doing using wireless sensors. So this sensor data, if there is a way for us, and this we already have found a way to make this data from this particular brain, if we can continuously feed this, where we record all this data at the or vehicle level. I'm talking about recording, just like a black box. See, black box, you know, in very much in flights, a black box records every single movement. Similarly, we are trying to create a black box of all sensor data within that particular car. So now this is a project which we are taking up on behalf of our company. We are doing this research there so that we can do a sensor failure prediction at a car level. So this is an ambitious project that we have taken up. We want to create a black box even for an autonomous vehicle, so that this all this electronics data, see, it's not about sensors alone, it's also about camera data. So all this camera data is coming, all this sensors data is coming. What's happening right now, it's a temporary memory. They're not getting stored, it's automatically getting restored. So but we want to store it for the future. We want to, because then our data, I mean, a black box to be operated. So this black box can sit somewhere outside the car instead of within the car. That's our logic. We don't want the black box to sit within the car because there's a huge bandwidth available. We want this particular thing to send all this data outside so that we can do a sensor failure prediction much earlier than before the sensor actually fails. So this is a sensor failure prediction which we are doing in autonomous vehicle. So normally sensor failures, when you talk about, you only talk about automobile assembly or in wind energy or say in factory automation. But these days we are using sensor failure prediction even in automobiles, even in these electronic items, just even in your high-end industrial items, wherever the electronics is involved, we are definitely using these sensor predictions. So what we use, where do we train these models? So we have trained these models on actual data sets. So we have enough data sets from NASA, from SECOM, We have got enough data sets. In fact, Madam was asking for a data set. So in fact, SECOM and NASA is one place we definitely search for a lot of data. But there are other areas where we can get a lot of data. So we use an LSTM for training the model. Then we deploy it in a cloud and build a real-time alert system. So this is another area which we are doing it. And most of the industry employees who are hiring for this particular skill, even in India, TCS is hiring, Honeywell is hiring, Infosys Cobalt is hiring, ABB Robotics is also hiring. So this is what we normally you are using in predictive maintenance as well. What are the sensors which we normally do that? I mean, which sensors do we use? The temperature sensor, the vibration sensor, the pressure sensor, the current and voltage, oil sensors. So oil sensors we are not talking about here at this moment, but what we are actually looking at are the cameras part. So our more interest was in looking at the cameras part. So the cameras and the radar signals, so that's our interest in autonomous vehicle. We want to capture that part. But yes, of course, there is enough scope even for the temperature or the vibration sensors within an autonomous vehicle, go outside the autonomous vehicle and check this part. See, the pressure and all, they are already being mentioned, already measured within the autonomous vehicle, not just the autonomous vehicle, every premium vehicle has got a pressure meter now. So, I mean, that and all is already doing it. So what are the core AI techniques which are used? Obviously, RNN will be used, LSTM will be used, classification we use mostly random forest methods. For anomaly detection, we use outliers. So these are the core AI industries where we are using this. Anyway, I'll just go complete this part as well and come back to our AC presentation. You're done this. So that is as far as AI, I mean, autonomous vehicles is concerned. Now, the second part of this presentation was agentic AI. So I need to give a basics about agentic AI, and you have already seen what's an agent. So this particular component of an AI agent, when it comes to actually you're talking about ECE part, so we need to focus on that. So for us, an agent, as I said, any a particular autonomous software or hardware that can perceive, make decisions, act towards achieving a goal, automatically independent, and it can interact with other agents. So in traditional system, it's a linear process, but in an agent's environment, let me, before I talk about agentic AI, I'll give a very brief introduction about agentic AI directly from a market leader. Let's look at a market leader talking about agents, then I'll talk about agentic AI. And that market leader is obviously Satya. So I'll just share a brief 1 minute audio brief from Satya. So then I'll explain the basis of
the approach at least we're taking is, I think the notion that business applications exist, that's probably where they'll all collapse, right, in the agent era. Because if you think about it, right, they are essentially CRUD databases with a bunch of business logic. The business logic is all going to these agents. And these agents are going to be multi-repo CRUD, right? So they're not going to discriminate between what the backend is. They're going to update multiple databases, and all the logic will be in the AI tier, so to speak. And once the AI tier becomes the place where all the logic is, then people will start replacing the backends. The approach at least we're taking is...
so that was Satya Nadella, and let me just explain what Satya Nadella has said. So let me just explain what Satya Nadella said. Satya Nadella says, see, every single software system is just a database. And on top of this database, there is some business logic sitting. So it may be a CRM, it's their CRM is a database on top of which a customer relationship logic is sitting. When you talk about SAP, it's a database on top of which an enterprise resource planning is sitting, the business logic is sitting. When you talk about Gmail, Gmail is essentially a database on which the calendar and the meeting and this messaging part is involved. So every single software system is just an essential CRUD database, and on top of it, this business logic and I give it to the agents. Then it doesn't matter what the backend is, I can happily make everything really run. So this is exactly what agents do. And this is agentic AI. So agentic AI doesn't matter what the backend is. A lot of information comes from various places. We're not bothered about what's the backend part. We take information from one system, moving to another system without writing a single line of code. That's what agentic AI is all about. So now if you look at the components of an AI agent, so now if you look at it here, sensor, how the agent perceives its environment. It can be text, it can be images, or it can be data. The processor, the decision-making code. The actuator, which is the methods for taking calls. So the memory obviously for short-term and long-term learning. So now you're talking about multi-agent, which are, as I gave an example during e-commerce, especially festival season, that's where we use multi-agent because they have got much more autonomy. Now, if you look at where this particularly used in various areas, part, you know, for so agentic AI for autonomous vehicles. So where do we use it? For real-time decision making, for handling uncertainty, for multi-sensor coordination, for dynamic planning in traffic, for continuous learning loops. So when we talk about where agentic AI is used, then I need to really show where it's exactly being used. I'll show this autonomous vehicles. So traditional AI versus agentic AI. Traditional AI is static model. It only predicts. So agentic AI actually acts, plans, corrects, uses tools and external data, autonomous workflows. So the core components, perception agents, planning agents, control agents, safety agents, and communication agents. So autonomous vehicle stacks, if you look at 2025, sensing, localization, perception, prediction, planning, control, vehicle actuators. In fact, that's what I've mentioned little while ago. There are four brains involved here: the perception brain, the fusion brain, the prediction brain, the control brain. Sensing and localization, that's all this is being done. So agentic AI operates across these layers. So the role of the perception agents, we have already seen that it's processing all these inputs and it's passing the structured data off to the fusion brain. The fusion brain is detecting all this information and then it's passing on to the planning brain. So the planning agents are doing behavioral planning, they're doing the trajectory generation, they're doing the risk evaluation, they're doing negotiation with nearby vehicles, they're acting under charging traffic conditions. See, when we talk about autonomous vehicles, the biggest problem is we think autonomous vehicles mean only Tesla self-driving cars, and that's the difference which we need to actually differentiate. Autonomous vehicles is not just Tesla self-driving cars. There's a bigger industry of autonomous vehicles, and that is one thing which many don't understand. And that's exactly what I wanted to present today. You need to understand that the industry of autonomous vehicles is much different, much bigger, and this is what we are looking at. So let's take out this traffic part in public transport. So now if you're looking at in public transport, we already have already in China. In China, this is a fully autonomous vehicle and it's a self-driving bus. So this self-driving bus automatically has it. Now happily this vehicle is moving without driving vehicle. Bus is already a reality and all this automatically comes under autonomous vehicle. So the general perception we in India think that autonomous vehicles means only these cars, but autonomous buses transport, when you talk about public transport, See, many of these Australia, we have got these train systems where you don't need to actually swipe through. Now, normally in metros in Hyderabad, what we are doing, we are scanning through our camera, sorry, our cell phone, or we are scanning that particular ticket. Now, in these areas, you are not using any of them. In Australia, you have these metros where you don't need to do that. Automatically, it scans, your face gets scanned. You don't need to put that particular QR code out there for scanning. So that's happening already in several places in public transport. In Australia, we are doing it. And not just in Australia, there are other places which we are doing it. In fact, there's a problem in video. I'm not able to open it. Uh, let's see if I can open it. Okay, that's not opening. Fine. So another area which you saw earlier in sense. So this driver fatigue is electronic sensors are predicting wherever the driver is automatically getting sleepy. The sensor just, giving indication. ఓకే చాలా వీడియోస్ ఉన్నాయి మేము అందుకని కంటిన్యూస్గా ఓకే yes.
Attention, signs of fatigue detected. For your safety,
And again, this is not just in one part. You got sensors doing a lot of heavily using it and affecting what kind of scenarios can happen.
Excuse me, sir.
Sorry about this huge disturbances. There's a big bandwidth issue here. So even in logistics, we are talking about driverless trucks. we are not just talking about driverless cars. We are talking about driverless trucks. It's going on. Fleet management is happening without any trucks, without any drivers. So this is happening already in the US. We are happily driving wheel long vehicles. So 24-wheel long vehicles are happily driving without any. Ma'am, Hemalata, ma'am, actually you have my presentation. I already sent it.
Yes, sir. I have your presentation, sir.
So quantum navigation, which is heavily being used because we are talking about a zero drift navigation. So this zero drift navigation is possible only through quantum navigation. So wherever the GPS fails, we happily move to quantum computing. So AI is correcting small drifts in quantum inertial sensors. So continuous fusion. There's no stoppage in between. That's why we are using quantum sensors. Again, quantum sensors are again an EC domain. So that's another domain which is getting very much fast. I'm not playing any videos because AI videos is totally stopping up. So now the third part in autonomous vehicles, you're talking about autonomous trains. Auto is now around 15 kilometers. It is operating driverless
Excuse me, sir.
trains. And this is the first thing.
Sir, your voice is not clear,
We are
sir.
not too far away. India is also moving in this particular direction. So even in Delhi Metro, we are operating this. Trains in the Delhi Metro. The airports also we are using.
फ्रेम लावायचे पण आता मुंबईला कोण
Where multiple trucks are operating side by side. There also in fleet management also we are doing this using AI sensors and autonomous freight terminals, even AI parking, if you are using heavily. AI is being using for parking management as well. So remote operations centers, continuous driving, AI for fuel and route optimization. That's also being done by sensors. We are using a lot of the sensors data, even for fuel and route optimization. So AI in trucks, we are using there, and delivery robots is what I was talking about. I'll just show this delivery robots online. Thus again comes under autonomous vehicle because there's a lot of electronics even evolved there. And let me tell about the delivery robots. They are replacing entirely the human delivery agents in US today because these delivery robots are delivering at exactly 18 seconds, 18 minutes, whereas a human helper is assembling at around 30 minutes. So because of that huge 12 minutes gap, all those Zomato, Swiggy drivers in the US are being replaced by these delivery robots in the US. So delivery robots are becoming a rage in the US at this moment. I think there's a bandwidth issue, not able to open here. And these delivery robots, by the way, they don't use GPS. They use quantum navigation. This have 3 qubits in each of these delivery robots. So the 3 qubits give us around 8 routes, and those 8 routes are what are pursued by these delivery robots. In fact, it's in so these are the delivery.
Sir, screen is not visible, sir.
So these delivery robots. So that's a difference between normal ones and using quantum navigation. 18 minutes precisely when compared to 13 minutes of humans. So the delivery robots are again. So these electronics will determine where this particular thing is going. The next one area we talk about autonomous vehicles. You're talking about also warehouse robots, not just trucks. You're talking about warehouse robots as well. Cameras, the robot, all these warehouse robots are using lidars for cameras to move through. In fact, Walmart has replaced 1 lakh cargo, 1 lakh humans. It has totally automated it by replacing it with 8 lakh robots. 8 lakh warehouse robots are doing the same work which nearly 1 lakh agents were doing hitherto in Walmart in the US. So that's the kind of movement which is coming in automation using these autonomous vehicles, especially the sensors data which is being processed by AI systems. So it's a combination of AI and ECE. All this sensors data is coming. This sensors data is being fed autonomous navigation. We are using lidar plus cameras. So this AI arms are automatically identifying systems, the scanning the autonomous delivery or autonomous through model training plus ECE sensors. So there is an ECE sensor which is involved in this, taking the data from the sensor. Cars, be it trucks, be it trains, everything is being driven by a combination of ECE. That's ECE sensors and cameras are sending information to an AI system. The AI system is either a CNN or a vision transformer. This transformer or AI system is processing it, then sending it to the planning brain, which is the brain. The fusion brain is sending the planning brain, and then it goes control brain. So the brain is automatically processing it, it's happily making the movement. For this whole part, this autonomous vehicle supply chain, this is all these systems applications which you are seeing, either be delivery robots or warehouse robots or driverless trucks. See, 24-wheel driverless trucks is real dangerous because without 10, unless like you don't have blind spots out there. Blind spots are real hard for a 24-wheel truck to identify. So in driverless vehicle, which is going there, And in fact, Walmart has already replaced several long haul trucks with with driverless driverless trucks, totally with this. Long haul trucks where drivers were earlier there are being replaced with driverless trucks. So it's if you talk about this Tesla self-driving car, you had around 8 cameras. Now you're talking about a 24-wheel truck. We have nearly 20 cameras involved there. 20 cameras capturing the entire breadth of that huge container wide trucks. 20 cameras are giving you images. And now you're talking about not just 20 cameras. In fact, the number of radars, number of lidars, number of ultrasonic sensors are almost 3 times more than that of an Tesla self-driving car. So all this information is again being processed. Obviously, a CNN can't handle so much. So for these autonomous trucks, we are using vision transformers. So vision transformers are processing all that system data, and then it's passing on to the control brain. Not just that, another autonomous vehicle is obviously drone. Drone deliveries are happening very much, very fast. Autonomous flights, obstacle avoidance. We are using an AI combination for autonomous flights. We are also enabling precision handling and last mile delivery also through drones. So all this is possible into a combination of EC plus AI. And innovations in mobility, obviously we are doing a lot of this. And again, as I said, it's a combination of multimodal learning where taking data from sensors, from cameras. So 2025 models, we use the vision transformers to fuse camera video, radar, lidar, GPS, IMU, VTS objects. So all this is totally entirely used using vision transformers. That's exactly what I was saying. Till 2025, we were using CNNs, but now we are using vision transformers. So next generation, because 6G is coming, so now what we are looking at more advanced technologies. We are looking at more better signals where vehicle to everything. We are looking at vehicle to everything that includes signals, pedestrians, cyclists. That also is coming V2X. V2X is in fact the next hottest topic in smart transportation. And obviously without electronics, that's also not possible. Coming up, autonomous vehicles. So if you look at the transportation tech stack, the foundation model autonomy, you're looking at end-to-end vision language models, which are providing the perception, reasoning, and the planning. And then you're also having an edge AI plus on-vehicle compute. On-vehicle compute, which is AI is running inside cameras, traffic signals, electric vehicle chargers. So you're looking at some new things which are coming. This is a 2026 innovation, IQ to Mobileye. So this is more powerful than your normal premium cars. Or normal all premium cars have got ADAS chip. This is more powerful, 4.5 times more powerful. It has got a 8 megapixel camera, and the can sense even wet roads. That's the biggest part, Mobileye's latest innovation. So this is automatically reading all this information, and it can even detect wet roads. So this is the 2026 model which is coming up. So these are all the new innovations which are happening in EC in smart autonomous vehicles. So smart infrastructure. Okay, we just leave this. Sorry. So about 20 more minutes before I move to quantum vehicles and electronics. Are there any other questions? I have share much.
Participants, if you have any queries, the forum is open for you. Please, if you have any queries, please raise.
Okay, participants, thank you so much, everyone. Thank you so much, sir, for your brief explanation on ASI, why and how AI has become an AC discipline, and what is the replacement of classical DSPs with AI-driven ones like ML-based channel estimation, AI-driven equalization, compression, ESIs, beam reinforcement learning, and the core companies list that you have given us on the idea on with AI driven communication, and how a little delay in small things can lead to in EC related things can lead to a various vast change in the entire AI world. And what is the agentic AI that you have discussed, especially in brief in the second unit, has made us aware of what is actually happening in today's world, sir, and its applications like in various fields made us to have an idea on everything that is happening right now. Once again, I would like to thank you so much, sir, for investing your time in this regard, and thank you for in detail explanation, sir. We were all very enlightened and would like to thank you once again. Thank you, sir.
And I wish to apologize first of all for the second session. In fact, I am in a college in college hostel, teaching at an college in Hyderabad. The bandwidth is a big issue here. I couldn't get stable bandwidth. Even my phone bandwidth is dropping, and that's the reason there have been a lot of drops. And I sincerely apologize for the disturbance caused in the second session. First session we didn't continuous disturbance. I sincerely apologize for that.
Still, anyway, you couldn't let it go, sir. You continued with the best we all of us could focus on. So, thank you so much once again for your contribution in this regard, sir. Thank you.
Yes. Any questions I would happily answer. See, autonomous vehicle is a big domain. We in the industry need lot of people in this particular area. In fact, just like in US, we are short of autonomous engineers today. We don't have people who understand autonomous vehicles. We have a lot of CSC engineers. They don't understand our domain. They don't understand deep reinforcement learning. So there's a huge gap in the autonomous vehicle industry. Electric vehicle industry is growing like anything in India. Autonomous vehicle, a lot of projects are coming to us from, I mean, not because you're not talking about Tesla. See, that's the biggest difference I want you to understand. We are not talking about Tesla self-driving cars. Autonomous vehicles means autonomous trucks, autonomous trains, autonomous delivery robots, autonomous drone deliveries, autonomous warehouse robots. Every one of them is autonomous. Every transport vehicle is becoming autonomous today. There's a huge, huge market, and we honestly are very short of people who understand this. We have EC engineers, we have CSC engineers, we don't have autonomous engineers. We honestly are requiring a lot of people. They have got enough internships, enough projects, enough amount to give as pay packages. Industries are ready, but we need market ready students, and that's the biggest problem. We are not getting them. So I sincerely request academia to please include autonomous vehicle either through value-added courses or FDPs like this, so that the students get trained and the industry really benefits. We are happy to provide internships. We are happy to provide internship leading to package to explore, and we have got enough companies which are willing to give these kind of an opportunities. Let me give a very small glimpse as well who is offering these internships. Give me a moment, I'll just show that because I've got another 5 minutes. So if you're looking at autonomous vehicles in India, Ola Electric is offering nearly some 75,000 rupees internship in autonomous vehicles. Bosch AI is offering this
Sir,
internship.
Sorry, it's not visible, sir.
Oh, sorry.
sir, can you?
Okay, I just a minute. Is it visible now?
Yes, sir. It is
Yes.
visible.
Who is offering these internships? Ola is offering nearly 75,000 rupees internship. Bosch is offering nearly some 50,000 internship. Ether Energy is offering around 35,000 internship. Nvidia is offering more than 80 to 90,000 rupees internship. See, all these autonomous vehicles, we require a different kind of specialization. So we don't need CSC engineers. We don't need EC engineers. We need autonomous engineers. See, autonomous engineers are people whose title is today, we have an AV perception engineer. See, as I said, all these new roles in AI are being created as we speak. See, these roles never existed earlier. See, when in India did we have an AV perception engineer? Has anyone even heard of an AV perception engineer? But today you have an AV perception engineer in India. You have a sensor fusion lead, and you have a motion planning AI developer. These tools, these AI, I mean roles never existed earlier, but these new roles are being created as we speak. So there's a huge demand for all these areas. We definitely require a lot of people from various disciplines, EC, electrical, all these three domains, because they have a lot of domain knowledge, they can actually move into this area. And the kind of projects which we look at, deep reinforcement learning for driving simulation, people who are doing lane detection and sign reading system, real-time object detection. Those are the kind of projects which we expect from our students. And the tools, Kerala, ROS, TensorRT, NVIDIA DriveWorks. NVIDIA DriveWorks, we need a certification, definitely. So these are the areas which you will be looking at. And it's not just about autonomous vehicles alone. If you look at other areas as well, we have got enough internships which are coming up. But we don't have people who are coming into it. See, if you take about VLSI, Cadence India is offering internships, ANSYS is offering, TCS EDA Labs is offering, Synopsys Hyderabad is offering. And you look about these titles, these are all new titles. The traditional EC titles are different from the AI titles. You have got an EDA plus ML engineer. You have got a circuit fault predictor. You have got a VLSI AI specialist. These titles didn't exist earlier, madam and sirs. These titles are being created. Right now, these are being created. And we require PyTorch, obviously, ANSYS, Sherlock for these kind of titles. When you talk about voice AI, there are enough companies which are giving those internships. Voice biometrics engineer. Did you even heard of the title earlier? But we have a voice biometrics engineer. We have a speech AI model developer. So many new titles which are coming, which are not even with the placements department has no clue about. We have got enough of these new roles which are coming up in the AI industry, and honestly, we are not finding people for them. And that's the reason instead of going for freshers, we are paying more extra to the experienced people and training them. So we are training the same people who actually don't have the domain knowledge. So we are training the same people in domain knowledge. That's the huge cycle which we are spending in the industry. So instead of spending a CSE engineer who has been hard and bred in CSE syntax, and I'm training him autonomous vehicle for 1 year, I'll happily take an EC engineer plus AI plus autonomous vehicle who understands sensors, who understands how to process sensors, how to do the sensor fusion. I'll happily take him. That's the kind of thinking which is there in the industry. We are happy to make colleges partner with these or industry participants as well. We are willing to give these internships. We are willing to give these high packages when the academia is ready. That's all I wanted to communicate. That was the main reason for this FDP. Also, I wanted to just share this. We are not talking about driverless vehicles. Delhi Metro has already showed driverless trains. See, driverless metro, who is going to be needed there? It's obviously an EC engineer who's going to be needed there. And India today, I don't know whether you know this or not, India just last month has already launched its first driverless auto rickshaw. Swayam Gati was launched by India last month. So Swayam Gati by Omega Mobility, I think, yeah, it was Omega Seiki Mobility. They have launched Swayam Gati. There is no driver. This auto is driving on cars, on busy roads. So I asked these same people, where did they train this particular model? It's an autonomous vehicle. So where did train this Swayam Gati? The Swayam Gati was trained in the busiest roads in Bombay and Delhi. That's how it got its model training. So these are all the innovations which are coming, for which we need obviously ECE engineers, but ECE engineers who understand also AI. So let me just show this Swayam Gati. So with that, I'll just end this. So this is our first autonomous auto rickshaw. India's first, not just India's first, it's the world's first autonomous auto rickshaw. So there's so much of scope. So thank you everyone for this opportunity. Thank you Vishnu ma'am for giving me this opportunity, and thanks all the participants for your patience.
Thank you, sir. Thank you for explaining such a lot of things very patiently. All the participants are also very patiently and eagerly waited for the concepts. Thank you, sir. Thank you very much, sir.
Thank you, ma'am. Good night, everyone.
Participants, tomorrow we have two sessions, session 7 and 8. Session 7, expert is Dr. Srinivas Talabatula, sir. He is Associate Professor, Electrical Communication Engineering, IISc Bangalore, and he will deliver the content related to the topic photonic ICs for quantum computing. It will be very much useful to you. And the continuation session by Malleshwara Valluri, sir. He'll give the hands-on training related to the topic. We will share the link and session details tomorrow as a gentle reminder to you, tomorrow by 4 o'clock in the WhatsApp group. And attendance link and feedback link was already posted in the chat box. Kindly check it once.